Okay, and this is the second video on motion with constant acceleration where we're using our kinematic equations. And we start off with jets at JFK International Airport accelerate from rest at one end of a runway and must attain takeoff speed before reaching the other end of the runway. Obviously, they're not going to take off, right? So our first part of this problem says plane A has acceleration A and takeoff speed V sub TO. TO stands for takeoff. What is the minimum length of runway, and it has delta x a, which is the distance for plane A, required for this plane. Give a symbolic answer. So we're not worried about solving for this problem. It just wants to make sure you know how to set these problems up. So we know there's going to be constant acceleration because if you've ever flown, even if you haven't, a plane, once it gets to its set point on the runway, the first initial end of the runway, it kind of sits there and then it starts to accelerate, and by the time you take off you've accelerated in the positive direction for the entire time. So constant acceleration. So we have plane A taking off. Let's break this down to its symbols. Let's look back for a second at the kinematic equations. And for the kinematic equations on this particular problem, we're dealing with acceleration, velocity at takeoff, and the distance that plane A attains. In these equations, it doesn't mention anything about time. In the problem, it doesn't mention anything about time, but in these first two equations, you see time. We don't have time. We're solving for the distance. Now, just remember, x minus x sub 0 is x final minus x initial. That's their delta x. Remember, delta just means the change. So the change would be the final minus the initial. So here, we're given all three of the variables that we had in the problem. We have velocity, we have acceleration, and we have distance. So this looks like the equation that we're going to deal with. So I've written it down over on the sheet, and I have basically your velocity final squared equals your velocity initial squared plus 2 times acceleration times the change in distance. So your distance final minus distance initial. So what I'm going to do is substitute in, because it gave us specific variables for that problem that it wanted us to put in symbol form. Let's go ahead and write those. So remember, if you have to refer back to the problem, velocity final was velocity at takeoff. At takeoff, that's your final velocity on the ground, right? So velocity at takeoff, sub TO for takeoff, equals your velocity initial squared. Well, if you remember, there is no velocity initial. You're sitting on the runway and you accelerate to take off, and you have no velocity initial. So I'm just going to consider that 0, and 0 times anything is 0. So we're just going to keep it out, and we're going to make that equal to 2 times the acceleration. A was what it said to use for acceleration, so that's fine. And then it said delta x a would be our change in direction. So this can also be written as delta x, and in this particular problem it said plane A, so we're going to make that represented right there. So our velocity final, velocity at takeoff squared, equals 2 times the acceleration times the change in distance for plane A. So however far it went times the acceleration doubled will equal your velocity at takeoff. So we want to solve this problem for the distance, if I'm not mistaken. Let's refer back real quick. And yes, what is the length of runway, minimum length of runway, delta XA, required for this plane? So let's isolate our length of runway, which is going to be the distance. So we just want to get distance by itself. How do we get rid of 2 times the acceleration? Well, divide it by 2 times the acceleration. So it cancels over here and you're left with that. So just to write it clean, velocity squared at takeoff over 2 times the acceleration is equal to the distance that plane A traveled on the runway. And that is your answer for 3A. Okay, now we look at part B. Plane B has the same acceleration as plane A in our first example, but requires twice the takeoff speed. find the distance, find the change in distance for B and compare with the change in the distance for A. So that runway, what they're basically saying is how much more runway it'll need. So let's look at it. Plane B has the same acceleration as plane A. So the acceleration is going to be the same. The takeoff speed is what changes. Now this is basically a conceptual problem. If you look on here, let's go back to here and let's look. We look at what we had for plane A. It says plane B requires twice the takeoff speed. So how much more runway will it need? How much more distance? Well, let's just say if you double this right here, if you double the velocity, what will happen to it? Hopefully you said it will be 4 times as much, because if you double V and then square it, that is 4 times as much as what it was. So in that case, if you need 4 times the takeoff speed and the acceleration is the same, then if you grow the numerator by 4 times, the answer will grow 4 times. So these are a direct correlation. The numerator is a direct correlation to the answer. So if you increase it by 4 times up here, this will increase. So your answer to B is 4 times the distance of A's runway. And if you're confused about that, let's look at a couple examples. Let's just throw some fictitious numbers in there. And obviously this will not be the speed that a plane takes off at, but I just want to throw some numbers in there so you can just see it. So we'll make it real easy math. Let's say our velocity at takeoff for this plane A is 5 meters per second. I know that's not correct, but let's just go with it because it's easy math. So let's just say for plane A, it is 5 meters per second squared and over 2A, and let's just look at what that equals real quick. That would equal 25 meters squared second squared over 2A, which would equal 25 divided by 2 is 12.5 meters squared second squared over A. Okay, so this is what we're dealing with as far as what the speed would be if you had the velocity squared over the acceleration. That would be what we'd have for a fictitious speed for A. Let's look at B now. Let's make B twice the velocity. That's what it asked us. So twice the velocity of takeoff would be 10 meters per second. Square that. And we have that over 2A. So that's the only part we're dealing with right here. I'm not worried about really solving it for the distance or anything. A is a fictitious number right now, so I'm not worried about it. But let's go ahead and solve for this. 10 meters per second. If we double the velocity, that's where we're at. So this would equal 10 squared is 100. Whoops, I'll throw an extra 0 in there. 100 meters squared per second squared over 2A. Then if we get rid of everything except the acceleration, we'll divide the 100 by 2, so that will be 50 meters squared second squared over A. And as you can see, 50 is 4 times bigger than 12.5. So that's how we get 4 times the distance, because if we work this math out, let's just say acceleration was 1 meter per second squared. If we use that, anything divided by 1 is itself, so this would be 12.5 meters. This would be 50 meters. That would be our distances. And this is 4 times larger. This one is 4 times larger than this one, which is why we said B would be 4 times larger than the runway distance of A. So hopefully that makes sense. If you have any questions about it, just ask me about it in class, but hopefully that cleared it up for you and made a little sense. Okay, and for the last part of this, it says, find the minimum runway length for plane A if the acceleration is 2.20 meters per second squared and the velocity at takeoff, our final velocity, is 95.0 meters per second. So what we need to do now is just fill in the variables with these numbers and solve for distance. So let's go over here. I've already written the equation out the way we had it before. Remember, this is how we had it. Velocity squared at takeoff equals 2 times the acceleration times our distance for plane A. So let's go ahead and substitute those numbers in, the numbers we had, and now I gotta look back real quick. 2.20 meters per second squared for acceleration and 95 meters per second for velocity at takeoff. So this velocity at takeoff would be 95.0 meters per second squared equals 2 times the acceleration, and I believe that again that was 2.20. Let's see, yes, 2.20. 2.20 meters per second squared times our runway distance for A. Alright, so we want to solve for what is the minimum length of the runway for this to take off. So we need to get distance by itself. So let's go ahead and do everything we can to isolate this. You can either bring it all over like this or figure it up 2 times 2.20 and then bring that across. Well, we know, hopefully you can recognize that 2 times 2.20 is going to be 4.40 meters per second squared. So I'm going to go ahead and divide this out by 4.40 meters per second squared. That will cancel that out. And then divide by 4.40 meters per second squared. And this will all cancel out on this side. And that will leave us with our minimum distance for the runway. Let's go ahead and do our math real quick. We have 95 squared, so that's 95 squared divided by 4.40. And that equals 2,051 meters. Alright, and the reason I know it's meters is because second squared is going to cancel out, and one of the meters squared here will cancel out. So that'll leave us with just meters. Okay, and if I look really closely, I have 3 sig figs on my numbers. I have 3 sig figs here. I have 3 sig figs here. So technically the answer should be 2,050. But if you put 2,051, I would not take off on a worksheet. 2,050 meters. And that's our distance for the runway on part C. The minimum distance it has to be. All right, thank you.